Can you hear me? Can you see me? Can you hear and see me? All right, Star Rider says yes. Hey Alex, blind developer Christian. Welcome, welcome, Yuga. Hey Alex Schwartz, a repeat offender. Elijah James, Andre, Abel, Muffindil. All right, good. So, today, folks, this machine, this new M1 Max and the M1 Pros are really starting to become more of a mystery to me. When we went from Intel to M1, it was pretty exciting. There was a lot of changes. There was a clear indication that this is going to be a better machine. Besides the Xcode builds that I've seen so far, I'm not seeing huge improvements. And of course, video editing and all that, yeah, that's all great. We've seen some impressive stuff on YouTube. But so far, if you see my JavaScript weirdness last week, some of you had suggestions. I appreciate that. Thank you very much. Today, I have a similar issue, and this might be just me. I don't know. But we're going to go through it, and hopefully there are some folks that are C++ experts, or maybe not experts. Maybe you know some stuff. But I'm going to show you this, and it's really odd. So, all right, we're going to start. Now I have a couple of things here. I have two machines. Let's see. I have my Intel machine, 16-inch, Core i9 right here. And I've got the new M1 Max machine, also 16-inch. So both of these are MacBook Pros. And what I'm running, Bryce says, I'm a C-, expert. That's great. We'll see if that helps us today. So here's what we're running today. If you've followed my channel for a little bit, you know I like to use this website. It's called Benchmarks Game. If you're not familiar with it, it's pretty cool. And it has a bunch of programs written by people that are contributing their time and contributing their programs to do these algorithms. So these are implementations of different famous algorithms. It gives you the code. It gives you how to build and run the code. So what we're doing today is Mandelbrot test, and that's the C++ variety of languages using the G++ variety of compilers. Okay. I've already done this, clearly, because you've seen the thumbnail. I'm complaining, and I don't know what's going on. So what I did, I'll just quickly reiterate what I've done so far, and then I'll demonstrate. So I copied this code. Okay, this is the Mandelbrot. If you've seen any of my videos before, I've done Mandelbrot quite a lot in different languages. This one is C++. Okay, so then I created a folder called Mandelbrot. I created a file called mandel.c++, pasted it in there, and we're ready to go. Now, the next set of instructions says you have to build it. So here is the command to do that using G++. All right, so I already have it built, but I'm gonna, well, if I rerun that command to build it, it's gonna write over this file basically. It's gonna delete the gpp run file and write over it. But you know what? Let's do it anyway. Here is my command. Okay, now what you're seeing right now is the Intel machine. And you'll also notice that I've changed the architecture from the command given here. Okay, right here it says you can specify the architecture which you want to build it for. So this is key, right? When you're on the Apple machine, you want to target the Apple M1 architecture. When you're on the Intel machine, you can target different processor types, or you can go generic and build for x86. So to view all the different commands that are available, or I should say supported CPUs, you can run this command, print supported CPUs, and this shows you what CPUs are supported on this machine. All right, so what I'm going to do is target this right here, x86 64. So if I run that and build it for that, let's see. So that's like right over here where I have Sandy Bridge. Instead of Sandy Bridge, I'm gonna say x86-64 and hit enter. And that's gonna build, oops, it's gonna build this file right here. Oops, not that one, this one. Okay, that one is a backup that I've built. We don't need that one. So this is the file that it's going to build, and it's just done it. It's just built it. In order to execute this command, this program, I should say, we run this on the command line. 16,000 is the parameter. Okay, so Mayur says March equals native. Interesting. Okay, we'll have to try that. Let me try that right now. Why not? I'm going to try it and compare immediately before even running it, because I haven't seen native before. I haven't tried it, I should say. Okay, so that worked. Cool. That's why I love doing these live streams, because we have people helping out here. I'm going to change that command that they recommend just for this particular test, because I want it to run just a tad bit longer, and I'm going to hide the output. Otherwise, we're going to have all kinds of stuff spewing on the screen. And I'm also going to start this off with a time command so that we see how long it takes. And we'll start off with 50,000. So I'm going to kick that off. And it's done in 4 seconds. Oh, thanks for that. I should probably delete that, Alex, so that I don't get confused again. So I'm going to run the one I just built, and that took 2.72 seconds. Big difference. So I'm going to delete that file so I don't make that mistake again. The backup file, that is. Okay. I probably built it using some different architecture. Okay, so that's 2.6 seconds. Cool. Now, I want to do the exact same thing over here on the other machine, the M1 Max machine, which is this one. Now, I already have this file here, and it's the same exact file. So I'm not going to bother going through the code with you because, well, that's not the point of this exercise. You can look up the code if you want, if you're interested. Okay, let's take a look at the available architectures on this machine, which is going to be a little bit different. Obviously, right? So we've got all the Apple ones listed, including Apple M1. All right, we've got, do we have that native one? We don't have the native one. So Mayur, if you got another suggestion for which architecture to use here, or how to do that, after I show my test, which actually is going to be slower than the Intel machine, I'm going to use Apple M1. Then we can try that. So I'm going to build it using what I think would be the obvious choice, and that's to specify the MCPU as Apple M1. And you can see that right here. If you try to run this using the instructions that they provide, using Ivy Bridge. Clearly that's not going to work because that's targeting an Intel processor. So let's build this like that, and I'm going to run it for 50,000 iterations, same as on the other machine, and that's the correct one. Let's do it. Okay. Now you see my problem here. We have 2 seconds on the Intel machine. We have 6 something seconds on the new M1 Max machine. Bryce says, can we assume that it should appear M1 Max or Pro instead of just M1? That's a good question. I don't know. Fairhat says Apple latest. I did try Apple latest, but we can do that as well to satisfy the curiosities. Oh. Yeah, it didn't work for me with Apple latest. Let's try Arch Apple latest. So that doesn't work either. Anyway, M1 seems to work, and I would figure that that would be here. Let's try march equals native 2 just in case. No, that doesn't work. So that command doesn't seem to work. That march command on the Apple Silicon machine. All right, let's see. What are you guys saying over here? So Bryce says maybe it's just not optimized yet. That may be true. However, why is it that Xcode projects work and build so much faster? There's got to be some kind of optimization going on over there. And I'd be really surprised that C++ is not optimized. So I'm guessing that I'm doing something wrong here with this command, and maybe there are special other flags that you need to do that. Now, the optimization question came up in my mind as well. And I thought, hey, why don't I try building it on the Intel machine, taking that built output from here, transferring it to my Apple Silicon machine, and then running it here and see if that's going to be faster or not than the natively built Apple Silicon version. So I did that. Let me share my results. Okay, so if we take a look at the files that I have available here, oops. This is the one I've just built on the Apple Silicon machine. This one is the one that I've built on the Intel box. As you can see, it's also much bigger. So I'm going to run this one now and show you what's going on here. Just so we have a fresh memory of this, I'm going to run the native one, the one I built for Apple M1. So that results in 6.6 seconds. And then I'm going to run the one I built for Intel on the Apple machine. .5 seconds. So that's pretty interesting, right? It's running faster using the Intel build. And to show you that it's actually running the right ones, I'm going to run this for a little bit longer so we can check activity monitor. So I'm going to do 100,000 here. So this is the native Apple one. If I run this, 100,000 should take a while, so we'll have a chance to look at activity monitor. And there it is. It's running under Apple architecture, taking up all the CPUs, all 10 of them. All right, there it is. Interesting. Now, I'm gonna, oh, it already stopped. That took 26 seconds. By the way, somebody commented that I'm not using my calipers correctly. I thought maybe we'd try to measure this history here. Let's see how long that took. 2.57 millimeters. All right, just kidding, folks. Let's go back here. And so that took 26 seconds, and that was running the Apple process. Now, if we run this one that was built for Intel, I just want to show you to prove a point here. This is now running under Intel. There it is. Also using up all the CPUs, but running under the Intel kind. And that took 13 seconds. All right. Now I'm going to look at the comments and see if you guys have any ideas. What the heck is going on here? All right, Andrew. Andrew says, you can check whether your binary or any binary, such as the compiler, is Intel or ARM with a file command to make sure you're not using the Intel binary when you think you should be using an M1 binary. I mean, I think I just proved it by running it and looking at the activity monitor, but that's an interesting thing. The file command. Okay, can you give an example of the command line? Because I'm not used to the file command. So let's see, file. What do I give it? Just a file name? Oh, I guess so. Well, thanks for the tip. There it is. It's actually ARM64. So that's correct. And then this other one should be x86. There it is. Any other ideas, folks? Alex Schwartz thinks maybe the benchmark is designed for x86. Yeah, maybe so. Maybe this is optimized for using hyper-threading. So, interesting point. I thought about that, and then I decided to test that out. So I went over here to my Intel machine, and what you can do here is pretty cool. You can go to Xcode comes with a set of applications you can use. So here's Xcode in my applications folder. Oh, thank you so much, Jerry. Really appreciate that. You can go to Show Package Contents. Under Contents, you have this Applications folder and then Instruments. So we're going to open up the Instruments panel. And then under Instruments, you have Preferences. And then you have all these different tabs here. And under CPUs, you can actually set the number of CPUs that you want to use for executing code. Huh. So now if I run this same command here, this is the Intel box just in case anybody's wondering. All right, so I've set it to 1 CPU. I'm going to run this code. Let's give it 100,000 so we have enough time to really check it out. And if we take a look at Activity Monitor now, we should see only 1 CPU using this. Yep, looks like it's only 1 CPU. And it looks like it's this one, Core 1. So what's really weird is that I tried the same thing on the M1 Max machine, the new one, and it's not letting me adjust the CPUs there. There's some kind of bug where the native tooling, and I'm a little bit annoyed at that. The native tooling of Xcode is not actually letting me change the number of CPUs. It's kind of a bummer. Anyway, you can do this on the Intel machine, and that kind of answers one of the questions. Let's see what you guys are saying here. Clearly it's taking much longer this time around. And you're probably wondering what I did with this information now that I know this. Alright, so it took 37 seconds this time around, only on one CPU. So what I did was I set it to 8, right? Because the other machine has 10. And if this one was set to 16, then maybe it works a little bit faster. But I set it to 8. And it still, I believe, finishes faster. So Francesco says it's a compiler optimization issue since the Intel version converted by Rosetta for ARM scored better than the native code generated by the compiler itself. Well, that's kind of odd. Yeah. So I think what we're in agreement here is that Apple M1 flag for the C++ compiler architecture is not going to really optimize your C++ code? Is that what's happening here? Anyway, this one finished in 17 seconds. So a little bit slower than when you have this to use all 16 cores. So there's only 8 cores here, but there's 16. 8 of them are real, 8 of them virtual. When I set it to 16, let's just do a little comparison here. That one is 10 seconds. So yeah, the optimization here is clearly happening when you have multi-threading going on and when you have virtualization of processors. It looks like it's a lot better tweaked so far on the Intel machines, at least with the settings that I am using. And I may be using the wrong settings. I'm not a C++ expert, so anybody in the comments, if you all have suggestions about these settings, let me know. So let's see what you guys are saying here. Bryce, I don't have the MacBook Pro 13. I have the Air, and I don't have this installed on the Air yet. But I could give that a try, perhaps offline, and see what the result will be. But, I mean, this is the M1 Max. Shouldn't it be top of the line right now? So far, maybe if you're doing video editing, which I also do, it works beautifully for that. But for this kind of stuff, I don't see a huge benefit right now. Now, I should say, if you're doing web development, so far, I would say if you have an Intel machine or if you have an M1 machine, then stick with that. But if you're going to be doing native app development, like iOS, I have yet to test Android, but I will be doing that. iOS is going to be faster on the new machines as well. And probably the Mac OS development as well. Let's see. Yeah, I mean, David says, I wonder if there are lots of loops, unrolling, reordering of instructions. Who knows? There's maybe some kind of optimizations going on that work better on Intel than they do on the new machines. Navneet says, which G++ compiler are you using? This is the default one that comes out of the box. I believe it got installed with Xcode. Andre says, after delete the define AVX, your should take new results. I'm not sure what you mean by that. Can you rephrase? Okay. Rubizon says, easy. Instruction set of x86 is larger, and so all kind of extra trickery is going on. Extra magic, folks. That usually explains a lot of things in what we do. Are you using Clang? Clang. I believe so, yeah. So underneath that command, I believe it's using Clang. So this is, so I have, I'm issuing the G++ command. Let me go back to that screen and we can try that. So this is, let's go to this new one, right? So for those of you that missed the beginning, I'm just going to show you the command that I'm using. This is the command I'm using. I'll just leave that on screen for a little bit. I mean, yeah, Balaz says, might be worth to test bigger project compile time, not the compiled code's performance. I mean, this is not a very complicated program, but it maxes out the CPUs, right? So what we're really testing here is the CPUs, the performance of the CPUs, not the compilation time. Nikita says, about Andrei's comment, there was a more detailed one above. Open C++ source file and delete define AVX section. Okay, where should I do that? In the new machine or the old one, or both of them? I guess I should kind of synchronize the code, shouldn't I? Let me take a look at that. Okay. I mean, are you familiar with this code base? Is that why? How do you know even where to go here? That's pretty amazing. I'm impressed if you picked that up just right now. It says define AVX section. So, I mean, I hate messing around with the code base because other people won't be able to reproduce it. But for the sake of this test, we could do that. Now, there's a lot of places here where AVX is mentioned. So not 100% sure. Delete 16 through 18. Okay. This, right? Is that what we're deleting? Okay. Let's see if that works. Well, it compiled. Trying to run it now and see what happens here. Hmm. 25 seconds as opposed to, I believe it was 26 before. Yeah. So we had 26 before that, and now it's 25. Not much. Not significant enough. Need to delete all defines of AVX, says Andre. Let's check to see for more stuff. So I'm guessing everything between line 170 and here. Okay. So I'm guessing that this code won't even run on the M1, right? If it's an Intel specific thing, right? Okay, well, let's see. I got rid of all the mentions, and I don't know if this will even build anymore. Hey, it built. Okay, let's see if there was runs. Okay. Wow, looks like we have quite a few C++ folks in the crowd, so that's good. This is 25 seconds as a result, folks, so I don't think that's really doing much on this machine. So, you know, this is an interesting puzzle, and I will drop a link to this in the chat, as well as in the description. So anybody that thinks of an idea after this, I could maybe do a follow-up video on this. Now i9 is already faster than the M1. Why would I go and modify the code over there? It's not going to be, you know, it's proving that it's already faster using this code than the M1 Max. So why would I delete this on the Intel machine? I mean, so the thing is though, if Intel has an option that you can turn on to make the code faster, why wouldn't I use that? Why would I want to cripple my Intel code just so that it levels up with the M1 Max machine? I want to use the maximum capacity that the machine has to offer and seeing what it's capable of. That's the idea here. If I can run faster code on my Intel machine, then why the heck would I even need the M1 Max? I mean, I don't really necessarily care about apples to apples comparisons all the time here. I want to see if the value proposition of buying a brand new machine is worth it for people, right? So thank you very much for that, Etienne and Kaio. Thank you guys. Appreciate that. Yeah. Well. I think that Apple, if they're going to compete with this new machine, they need to make the optimizations on the new machine instead of crippling the the Intel builds, right? By the way, Examos, I did try that. I actually built the executable here, and I ran it on the M1 Mac, and it was faster. It was faster than the native one, and it was faster than the Intel one. So yeah, even with Rosetta on the M1, whatever the optimizations are for that code, it runs faster on the M1 Macs. So maybe it's the test. Maybe it's whatever code is being used here. I'm not super familiar with all these libraries and all these imports and the C++ code base. So I'm gonna leave it up for discussion and do a follow-up. Hopefully I'll get some answers from all you folks. Maybe you'll get a chance to take a look at this. It would be awesome if we can solve this riddle. I'm just puzzled right now. Why the heck would this happen? So I know that Swift is the preferred language for Apple right now, but I mean, you can't just cripple C++ builds, or not optimize them, I should say, not cripple. So, anyway, some stuff to think about, right? So Francesco says, could you try another C++ benchmark to exclude that your source code is structured in a way to not get properly optimized by the code generator? I don't have another one. Let's see. I don't have another test handy right now. Okay, so Alex suggests, can you try running C++ basic code in a loop on each to see which one is the fastest? Yeah. We could do that. All right. Do you have a loop for me? I don't think I have a loop handy. And like I said, I'm not a C++ guru. So if you have something quick you can throw together, pop it in the chat, and we'll do it. Let's do it. That's what live is all about. C++ loop. Oh my gosh, this Intel machine is hot. I think I've already said that before. All right. Anybody have any loops for me to run? Come on, folks. I'm doing a Google search right now in case you're wondering. Like I said, I did C++ in college, so that was a while back. Thanks, Mike. Appreciate that. Yeah, you can hear the fans. I can hear it too. Believe me, it's pretty loud over here. Sort a billion numbers. I mean, I had it somewhere here. Let me see if I can dig it up. I already did this before. I just don't remember where it is. Okay. Huh. Did I just find it? I think I did. Alright, I'm going to need you all help here. Alright, I'm going to switch over here to my Intel machine where I found a quick sort that I did in a previous video. Can you all see that? Okay. I'm generating some numbers between 0 and 99 and then sorting them. That should do it. Look at that. Okay, that's let's try that. Why not? I already built it, it looks like. Ha. Oops. Can somebody throw down the command in the chat for building this thing? Well, that's an interesting theory. Andrew Dunbar, I have a theory that Apple purposely crippled some workflows on M1 to make native code almost as slow as Rosetta and Intel code. That's why M1 Macs get hot and use more battery when they run Intel code. Interesting. Thanks, folks. Ooh, well, that's not good. What the heck? Oh, I'm on the Intel machine, of course. It gets a little confusing here. And it gets hot, so the heat goes to my brain. Okay, let's try that. G++ main.cpp. And we're done. We got a main. Does it run? It runs. Haha. Okay, I don't want it to ask me. Well, it doesn't matter, right? Oops. Time main. Does it take the... Oh, no, it doesn't. Okay, so that took 1.98 seconds. So I don't want it to ask me. How do we avoid that? I don't want any input. A.out, not main. Okay, well, I ran the wrong file. Okay. Okay. Cool. Comment 84 and hardcode instead of CZ. Okay, let's do that. How about that? Is that gonna work? Yes. Okay, let's do the same thing over here on this other machine. Pretty cool. So I'm gonna go to CPP. Oops. Let's go with quick sort main.cpp. Yes. By the way, let's check that. Okay, good. Time a.out. I'm going to enlarge this number. It's a little too small. So we're at, oops, we're at, what is that? That's 100,000. Let's add a couple more zeros there. Can I do this in C++? No. I guess not. So we're at 100 million. Let's see how long 100 million takes. That can't be. Come on. Segmentation fault. It doesn't like that. Too much. Too much. Segmentation fault. Come on, folks. Okay. This is taking a significant time. That's good. So that's a million numbers. Okay. I'm going to do the same thing over here on the Intel box. We're going to go for 1 million. And let's build it. And let's run it. Time. Okay. Cool. So this is it. This is the moment of truth. We've got 15 seconds on the M1 Max. Intel is not done yet. 19 seconds. All right, I changed my mind. M1 Max is worth it. Buy it. Quicksort works faster. Okay. Well, good suggestion. I like that. I like that. It makes me feel better about my purchase. David says put in -03. What does that do? Is that during a compilation? Let's see. -003? Like that? What does that do? Enables all optimizations. Yes, it sure did. It sure did. We went from 15 seconds down to 2 seconds. Okay, let's do this on the Intel machine. I like this. Three seconds. Okay, it's faster. It's faster on the M1 Max. Let's do this one more time just for sake of repetition here. So we're around 3-second mark on the Intel box. Pretty consistent. Let's do it a few more times here on the M1 Max. 2.5. 2.5. Yeah. Cool. Okay. So, quick sort seems to be working faster on the M1 Max, but we still have that other issue with the compilation of that Mandelbrot algorithm from that particular benchmark case. So it might be that that program is using some kind of special optimizations. And for those of you that are interested in checking it out, benchmarks game -team.pages. Anyway, I'll throw a link down. This is what it looks like. They've got a bunch of other stuff. Since we're here and we're looking at this, I'm planning to do a bunch of these other ones. And now I'm not super confident about the results. Ugh. But anyway, we'll see. Thank you so much, folks, for coming and for all the help on this C++ stuff. I'm rusty. We'll do Rust also. All right, folks. Appreciate you all. And I'll see you next time. Cheers.